guys, today our video is going to be about centripetal force. So today in class I taught you guys that centripetal force is mv squared over r, which is the same thing as ma, right? It's just that now since the object is moving in a circle, its acceleration is centripetal acceleration. So today in the video we are going to go through a couple of problems, how to use centripetal force, some very specific cases and scenarios, and then that's all we're going to do. So there's no PowerPoint for this, it's just going to be me drawing a couple pictures and working some problems. So the first thing I want to start with is a vertical circle. So let's take a look at what we did in class today with our bucket of water, right? And this bucket of water was twirled in a circle. That's kind of a bad circle, but that's all right. And in this bucket, I want to look at two specific points. I want to look at the bottom of the circle. I also want to look at what's happening up here at the top of the circle. And we can talk really briefly about the side here too if we need to, or if we have time. But I really want to look at what's going on in these two positions, at the bottom and then up here at the top. And we're going to draw some free body diagrams because centripetal force is a force, right? So we need to talk about that and how to find out using a free body. So let's look at this first case, which is when the bucket is down here at the bottom of the circle. So I'm going to draw a free body for that. I'm going to say that's the bottom of arc, right? Because this whole thing right here is an arc. So here's my bucket. So what forces do I have on my bucket? Well, I have the weight of the bucket going down. And then, oh, I drew that a little too long, so I'm going to erase this. And then I also have an upward force, right? So some people will say that that upward force is your centripetal force. And so some students will label it like this. That is not correct, because centripetal force is a net force. So Fc equals a net force. So what does that mean? That means that centripetal force is not an individual force that you put on a free body diagram. Rather, it is the sum or the total of the forces that are acting on the object. So here at the bottom I have the weight, and then I was pulling upward on a rope, right? So that force going up should be a little bit larger than your weight. Is your tension force. So this is what your free body diagram would look like for the bucket at the bottom of the arc. Now your centripetal force then would be your tension minus your weight. Because the difference between these two forces, whatever is left over, is going to be what's responsible for making the bucket turn in a circle. That's going to be your centripetal force. So if I wrote this out, centripetal force is mv squared over r. It would equal your tension minus your weight. All right, so let's look and see what's happening at the top of the arc now. So top of the arc, here's my bucket. I have the weight of the bucket pulling down. I'll draw my vectors a little smaller this time. But I still have that tension force, right? But now the tension force is going to be acting in the same direction as my weight. Tension. So now I'm going to have two forces that are pulling down to keep the bucket going in a circle. So at the top of the arc, my centripetal force would be my tension plus my weight. mv squared over r equals tension plus mg. All right, so the question that needs to be asked, or that some questions will ask you guys, is what is the minimum speed to keep the bucket going in a circle at the top? Because if you think about it, if the bucket is not going fast enough at the top, to maintain that circular motion, then what's going to happen? Well, it's going to fall. First of all, it'll fall straight down, right? It won't be able to keep that trajectory, that circular motion happening if you're not going fast enough. So that's a really common question, and so to find it, we're going to look at what's happening at the top of the circular path with the bucket. Okay, so this minimum speed is sometimes called the critical speed. And you guys will see this question asked a lot with regards to like roller coaster rides and all that stuff. So critical speed is has to do with the velocity that it's going at the top. And that's always going to be when your centripetal force equals the weight of the object. So mv squared over r equals mg. So we have m's on both sides. So we get v squared equals gr, and v equals square root of gr. So really the minimum speed has to do with what size of circle you're trying to make, right? So the object has to be going at least this fast in order to maintain the circular motion at the top. Any faster than this, fabulous, wonderful, but it has to be going at least this fast. Okay, so let's look at a roller coaster where you have a cart and it is going, has a point at above in a loop and then a point below at the bottom. So what we just did for a bucket applies to a roller coaster going through a loop as well, right? We have our, except now it's not tension that is helping us provide our centripetal, it is the normal force, right? And then this is the weight. And then up at the top, we have the normal force and the weight. So what do I mean by normal force? I mean the normal force between the track and the cart. Here, and then again, the normal force between the track and the cart pushes it down and helps contribute to the centripetal force. So, same exact formula, same exact situation. So let's look at a car. Now we're going to look at two different situations. One when the car is going through a dip or a valley, and then one when the car is going over a hill. So these are obviously very exaggerated, but here's car 1, and then here's car 2. And we're going to talk about what's going on in each one of these things. Okay, so car 1, as it goes through this dip or valley. So it is making a circle. It's making a centripetal motion, right? It's making half of a circle, but it is a circular path here. So we've got a couple of things happening. The car has a velocity that's going this way, but its acceleration, remember, always needs to be pointed towards the center of the circle. So that means that it's experiencing a centripetal force towards the center of the circle as well. So let's draw a free body for this guy. So this guy would have the weight of the car, let me reset, the weight of the car going down. But it also has a normal force, right? The normal force between the car and the road. And that upward push should be much larger than the weight, because normal minus the weight, in this case, will give you your centripetal force. So same idea as your roller coaster and as your bucket of water. When it's at the bottom of the loop, whatever's pressing up from the ground has to be much larger, or it won't go in a circle. So now let's look at the opposite situation when it's at the crest of a hill. And when it's at the crest of a hill, what you have is you have weight going down, and you have a normal force going up. But this time the normal force is much less because the car stays on the road, right? It is making a circular path, so that means that the net force, or the centripetal force, must point towards the center of the circle. And that means that in order for that to happen with the circle that it's making, the weight has to be larger than your normal force. Weight minus normal, so mg minus n equals mv squared over r. Okay? So those two situations are pretty common in in a lot of circular motion problems. All right, so now let's look at the situation where a car is going around a curve. So we talked about this kind of briefly in class today. This is going to be like a top-down view, I guess. Ooh, that's a terrible car. Tire, 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 tire. All right, so let's draw some vectors to kind of describe what's happening here. The car has a velocity, remember, that is going tangent to the circle. So here's your velocity vector. And then we also have an acceleration that is pointed towards the center, which means that we also have a force that's pointed towards the center of the circle. So we talked about how in this case, when a car is taking a corner, centripetal force is your friction, right? Your force of friction. Friction is what is responsible for keeping your car in this curve. If you didn't have any friction, if the roads were slick or wet or icy or your tires were worn down, your car would not be able to grip the road, and so your car would spin out and follow this velocity trajectory. It wouldn't be able to stay in the appropriate path. So remember that friction is equal to mu times normal. Friction is equal to mu times normal. So that would mean that your centripetal force is equal to mu times normal. And in this case, your normal force, since the car is on a flat road, the normal force is just the weight of the car. So we can cross out some values that are the same, which is the mass. And then we get v squared over r equals mu g. So a lot of questions tend to revolve around the idea of how fast can a car go to make a particular curve, right? And this is what a lot of highway engineers are also concerned with. So to find your speed, it would be the square root of mu gr. So this ends up being the minimum amount of speed that a car needs to have to navigate the turn of a particular radius.